Welcome back, AP Statistics. This is Chapter 4, Understanding and Comparing Distributions. Quick note on percentiles. We're going to start our section here with a discussion on percentiles before we get into the bulk of the lesson. A percentile is a measure of position within a set of data, and it says what proportion of the data is below a particular data value. So for example, if a data value falls at the 80th percentile, what that means is that 80% of the data would be below it. So that means quartile 1, Q1, marks the 25th percentile. 25% of the data are below it. Q2 marks the 50th percentile. It's the median of the data, 50% above, 50% below. And Q3 marks the 75th percentile. 25% of the data are above it, 75% are below, so that means it's the 75th percentile. Note that a percentage is a proportion. It's a part-to-whole analysis. If I'm talking about 80% of the data, I'm talking about 8 out of every 10 data values. Okay? That's a part-to-whole analysis. A percentile, however, is a position within the data. All right? It talks about where do the data values fall relative to others. All right? Where does our data value in question, represented by, I guess this is you here, relative to the rest of the data? It's a measure of position for your data, not a part-to-whole analysis. Okay, so percentile, measure of position, how much of the data are below you, or a data value that's important to you. Okay, now we are into the bulk of the lesson here. We're going to be talking about a graph concerned with the big picture of a scenario and talk about what it does well and also talk about its limitations, right? So here we have the average wind speeds in Hopkins Memorial Forest, that is in the USA. Very good. We have a 5-number summary over here, and we have our histogram and box plot. So what do we know about the graph to the right? And by graph, I mean everything that's going on here. 5-number summary, box plot, histogram. What can we tell about it? And we note that n is equal to 365. Okay, so when we are given quantitative data, we want to cuss. All right, so we're going to get to each of the letters of the acronym cuss, right? First, we are observing a distribution of average wind speeds over the course of a year, hence the n equals 365, not a leap year, incidentally. So we have a measure of center, and that center is the median. Now remember, median is a good measure of center in this case because this is going to be a right skew curve. All right, as we can clearly see in the histogram, the curvature of this would be right skew. Okay. Unusual features we see in the box plot. There are several outliers. Specifically between 5 and 6.5 miles an hour. Oops. So the shape of the data would be right skew. Right skew, we have the bulk of the data on the left-hand side, but we have a long tail out to the right, so it is right skew. And we are now going to talk about the spread of the data. We have quartiles 1, 2, and 3 right there, so we can have the interquartile range between Q1 and Q3. If we were to do Q3 minus Q1, we would get 2.91 minus 1.42 is 1.49. So the interquartile range is going to be 1.49. Okay, so that can be part of our measure of spread. We could also talk about the range of these data. All right, the range we've talked about has some pitfalls, but it still may be a bit useful. Our max wind speed is 6.17, and our min wind speed is about half of a mile per hour, right? A little more than a half of a mile per hour. So that's our range. 6.17 minus 0.58, whatever that is, that would be our range, max minus min. All right, so those are some measures of spread as well. Now, what might be nice to know about the data set that cannot be determined from the big picture graph? Well, one thing that might be nice to know is there a particular time of year in which these outliers are more likely to happen? Are there other times of year that the wind is especially slow for a long period of time, which would make for these taller bars on the left-hand side, right? And the way to do that is to break up these 365 days according to their seasons, all right? Are there a few high wind speeds spread throughout the year, or are they isolated to only a few seasons? All right, we want to talk about the seasons. So can we break this big picture graph into graphs denoting seasons? Okay. All right, so here are our graphs talking about seasons. All right, and we can see right off the bat that there are some noticeable differences between the seasons. It is more interesting to divide the data into several seasons. We can see that the high wind speeds did not happen in the summer. The summer was pretty boring wind-wise. Also, we can see that almost all the outliers occur in the winter. And for whatever reason, the windiest day is actually a day in the spring. It's kind of an anomaly over here. That's the fastest wind speed of the entire year. That's our 6.17 miles an hour from the prior slide. But most of those outliers actually happen during the winter. Okay, now we're going to analyze multiple data sets with a stem and leaf plot. The stem and leaf plot to the right, this guy right here, features data from the nest egg index. All right, that's a way of measuring the quality of a long-term investment in all 50 states. The mean is 100. Okay, so we're talking about investing here. Describe the distributions of both the South and West and the North and Midwest. And what we're going to be doing is talking about the shape of the distribution, and we're also going to find the median to measure the center. All right? And what are the key differences in the distributions? If we find the shape and center, we have enough information to talk about the differences. Okay, so you give this a go. Talk about the medians of both of these sets of data, South and West, as well as North and Midwest, and talk about the shape of each of these data sets, and see if you have a good idea of how they compare. Unpause the video when you are done. All right, I'll assume we're ready to go on. So talking about the center, the South and West have a median of 87. Okay, if we were to count to the middle to find the median, we'd have a median of 87. North and Midwest have a median of slightly above average. Very interesting, 103. So the center of North and Midwest is pretty significantly higher than South and West. Let's talk about the shape. The South and West fit a bell-shaped, that is unimodal and symmetric distribution. That's just about as close as you can possibly hope for in real-world data for a bell curve. That is that's very close to a perfect bell curve right there. While the North and Midwest fit more of what you might call a left skew distribution. Keep in mind, this refers to 88, 90, 93, and so we're going up in the numbers as we go down the graph, okay, down the chart. So that being said, the bulk of our data would be on the upper end, 100 and up, with a couple of lower values in the North and Midwest. Yep, so we would say it is left skew. So the distributions are a little different as well. All right, we're going to do the same thing now, but with box plots, and we're going to talk about roller coasters. What else? Roller coaster riders want a coaster that goes fast. Well, at least most people. Maybe that's what this footnote says. There are two main types of roller coasters, those with wooden tracks and those with steel tracks. Do they typically run at different speeds? And here are box plots. We have a bunch of roller coasters plotted here. Here are the wooden roller coasters, and here are the steel roller coasters. We are going to compare the speeds of wooden and steel roller coasters. Specifically, we're going to be looking at these box plots here, and we are going to use CUS to compare the steel and the wood roller coasters. Okay, so pause the video, see if you can compare these data sets using CUS, and unpause the video when you're done. Okay, let's hop to it. The center, the medians, are both slightly above 50. They're actually not terribly far away. Here's our median, just a little bit above 50, say, I don't know, 54, 55. And this may be slightly higher, this median, but not by much. They're at about the same spot. Unusual features, all right. There is absolutely nothing unusual about our wooden roller coasters. They are quite reasonable, very reasonable data. The steel has outliers. I don't know what kind of boring person made this roller coaster, but here we are, about a 10-mile-an-hour kiddie coaster down here. And then we have this fella right here, which is, I guess, important enough to get like a little star instead of just a dot. That would be the Formula Rasa in Abu Dhabi, United Arab Emirates, which as of 2024 is the fastest roller coaster in the world. Record previously held by King Ka at our own Six Flags Great Adventure in New Jersey. Right? So, steel has some outliers. We got really fast steel roller coasters that put the wooden roller coasters in the dust. And we have this almost embarrassingly slow steel coaster, which, I mean, why? All right. Both are unimodal and symmetric, barring outliers. All right, if we were to consider these outliers over here, we could make an argument that the data are a bit skewed to the right. For steel, we have a couple of high values that skew things to the right. However, if we were to exclude outliers, and they are outliers, they stand far enough away from the bulk of the data that we acknowledge them as such, both seem to be unimodal and symmetric. 50% of the data are gathered very close to the median. The middle 50% of the data are, again, gathered very close to the median, and 25% at the extremities stretch out a little further. All right, so both seem to be rather unimodal and symmetric, barring the outliers that we see in the steel roller coasters. All right, and now we're talking about the spread of the data. Steel has a greater range and interquartile range, much greater range for the steel roller coasters. Interquartile range is also slightly bigger. So our measures of center, interquartile range, and range in general are both bigger in favor of the steel. Wooden roller coasters are more predictable, all right? They stay within a much tighter range, okay? Now you'll notice that there's one measure of spread I have not mentioned, and that is the standard deviation. Well, in order to know the standard deviation, you need to know the mean, and we don't know the mean. We know the median, which is not necessarily the mean, right? So we need to look at what we are given and CUS with what we're given, okay? So that's why I have not talked about standard deviation. That's why I haven't talked about the mean, because I literally have no way of knowing them. Okay, now we're going to talk about travel. Here we go. The Bureau of Transportation Statistics of the U.S. Department of Transportation collects and publishes statistics on airline travel, right? Here are the three displays of the monthly percentages of flights arriving on time between January 1994 and June 2016. Okay, so first question, describe what the histogram says about on-time arrivals. Now, to do this, we could use the acronym CUS, talk about center, see if there are any unusual features, and then we talk about the shape and the spread of the data. Okay, so let's see how we can do with just the histogram. Okay, with the histogram, we can see that the shape is, of course, unimodal and symmetric. We can get a good idea of what the range would be. It would be about 90 minus, here is 65, 60, somewhere in there. So the range is about 30. All right, the range would be about 30. Interquartile range, you can't really tell that easily from the histogram. It would be a lot of work. But we have an idea of what the range is. So those are the two S's of CUS. The center is going to be somewhere around here. This is our modal class right here, the class of greatest representation. And it's looking to be upper 70s, all right? Maybe it's in this block, all right? It's somewhere in this neck of the woods, okay? So our median is going to be somewhere between 75 and 80, okay? And unusual features, honestly, this looks like a pretty tame bell curve. Some folks down here, just looking at the histogram, might be outliers, but I don't know. I don't know. So that's what the histogram says. What does the box plot of on-time arrivals suggest that you cannot see in the histogram? So here's my box plot. Here's my box plot. And what I can clearly see right off the bat are these outliers right here. Those are not obvious in the histogram, but I do have some outliers right here, some outliers. What I can also very easily tell is what the, a good approximation at least for the interquartile range. We have about 70, I don't know, 75 and a half, all the way up to Q3 looks to be about 82. So yeah, those Q1 and Q3 could help us find an interquartile range. All right, so it's like 6 and a half, somewhere in there. And that would be virtually impossible to tell without a lot of effort over here in the histogram. All right, so those are some things we can see in the box plot pretty efficiently. Number 3, describe the patterns shown in the graph showing box plots by month. At what time of year are flights most likely to be late? Can you suggest a reason for this pattern? Well, note this is a percent on time, all right? So take a moment, look at all of these little tiny chunks of the year, months of the year, and you tell me, how would you answer question number 3? Okay. Maybe you have an answer, maybe you need to pause the video, look at it a little longer, you do what you need to do, but let's talk about this. I'm looking at January and not February. February is a little variable as well, but especially January and December, all right? And also maybe June, all right? But definitely January and December. The percent on time has a very wide range and dips pretty low for some months. No outliers, but it does dip pretty low. What's the deal? Well, something happens in December, and something else happens in the very beginning of January. Those things are Christmas and Easter, respectively. Also, the season in which Christmas and New Year's happen is the winter. It's the very beginning of winter, okay? So you got your bad weather and you got your festive occasions, all right? So that is a recipe for a lower proportion of on-time flights than at other points in the year. What's going on with June? Well, 2 words. Summer break, all right? Summer break is happening in June. Everybody wants to get out for a vacation. People just cannot wait. And then again, you see some lower percentages of being on time. All right, so things happen throughout the year and our data are testament to that. Now we're going to be making some box plots on the calculator so we can compare data efficiently on the calculator. So we're going to consider the data for the number of bugs caught by the group of children, and now we've divided it up by your boys and your girls by creating box plots on the graphing calculator. If you want to look in the book, instructions can be found on page 83 and 84. We're going to compare these data sets with CUS, but first we're going to graph them both in the calculator. See you at the calculator. Okay, here we are at the calculator. As per usual, we go to Stat, we go to Edit, and we enter our data. I have list 1 for the boys and list 2 for the girls. Right? I've listed out all of my data values. Very good. Now I'm going to go into second stat plot. Again, a familiar place to be. Okay, so we have plot 1 on, and that is going to plot list 1. I'm going to go down to plot 2 now. I'm going to say plot 2 on. Go to my type. And I'm going to click this. Okay, very good. So just as before, I have a box plot that shows outliers. Now, I actually want this one to produce list 2. How do I get list 2? Well, you'll see above the 2, there's a little L2. Just like above the 1, there's a little L1. Okay, so I'm going to hit second and 2 to get L2. Now what I'm doing is I am plotting both of these box plots at the same time. Okay, so since both plots are on, I should be able to plot both at the same time. All right, and now I'm going to go down to zoom 9, zoom stat, and boom, I have my 2 box plots. Very good. So this first one here is my list 1 box plot, and down here I have my list 2 box plot. I can now compare these. The centers, the Q2s, are about the same spot, although the center for the girls is a little higher. Okay. The unusual features, not really any unusual features with the boys. With the girls, we do have one outlier, that data value of 12, if you recall. Okay. The shape of these data, all right, for the boys, the middle 50% are pretty far to the left. So you could make an argument that since 25% of the data are over this big span right here, and 75% of the data occupy about the same amount of space, that this is going to be a right skew distribution, all right? Ideally, we would want to see a histogram for that, but it's at least a good guess. Barring the outlier for the girls down here, someone was not too enthusiastic about finding bugs. But for everyone else, it looks pretty unimodal and symmetric. As for the spread of the data, the interquartile ranges are about the same. However, the range for the girls is pretty significantly bigger. Very good. We've compared the data sets using CUS, and we use the calculator to set things up. Okay, to round out our lesson today, we have one more graph, and this graph is called an ogive, not an ogive. An ogive. An ogive is a cumulative frequency polygon. What on earth does that mean? Well, a frequency polygon is like a histogram, except that instead of bars, frequencies are dots connected by segments, hence polygon, many sides or many segments. All right, so how do I read this frequency polygon that is apparently cumulative? Well, we're starting at $0. Pretty lame salary if you ask me, all right? By the time I get to $10,000, I have accumulated a frequency of 3. By the time I get to $20,000, I've accumulated 4 more for a total of a frequency of 7. All right, so by the time I get to $20,000, I've accounted for 7 in my sample. All right, by the time I get to $30,000, I've accounted for 13 more, so I have a total of 20 that I've accounted for already in my sample, and so on and so forth. All right? So we are considering a sample of size 100, looking at a bunch of different salaries, right? And we see that our ogive starts going up and up and up and then really plateaus by the time we get to our highest data values up here. Looking at the ogive to the right, we can actually pretty easily approximate Q2, Q1, Q3, and the interquartile range. I'll show you how to do Q2, and I'll give you a chance to try to find an approximation for Q1 and Q3, and then compute the interquartile range, okay? Q3 minus Q1, right? So let's see how to do Q2, all right? Q2 corresponds with the 50th percentile, all right? The 50th percentile. So I'm going to go to this 50 right here. This would be the midway point between the lower half of the data and the upper half of the data. It's our dividing line of our data. We have a total of 100 values. 50 is dead center. That would be my median, right? So what dollar amount does that correspond to? Okay, going to the right and then going straight down, I'm at about $45,000. So I could pretty safely say that between $44,000 and $45,000, somewhere in there, would be my median. Now you try to find Q1 and Q3 and then the interquartile range. Pause the video and then unpause when you think you have an answer. Okay, let's find Q1. Well, Q1 is the 25th percentile. So 25th percentile, 20% of the values are below that. Well, if I have 100 values, that would be value number 25 in the list. Okay, so here we go. Going to the right. Very good. And then going right on down. I'm at about the mid 30,000. All right, the mid 30,000. Very good. All right, now we have Q3 at the 75th percentile, so around 75, all right? 100 total values, around 75 would allow for about 3/4 of the data to be below it. Okay, so we're looking at 75, going over to the right here, and we land at about, I'd say about $62,000, all right? So that would be Q3. So then the interquartile range, you have 62,000 minus, I don't know, say 34,000. That would be 28,000 would be my interquartile range. All right, these are just approximations, okay? Does not need to be perfect. If the highest salary is 100 grand and the lowest salary is 10 grand, say part-time job, neither of which are outliers, we're going to create a box plot of the data from the ogive. See if you can do it now that you know Q1, Q2, and Q3, and now you have that 10,000 and 100,000. Pause the video, give it a go, check your work against mine. All right, I'll assume we're ready to go on. Here's my box plot. Compare your work to mine. Hopefully they look pretty similar. No dots at the extremities because there are no outliers in this data set. At least none that you need to be aware of.